Alright, so just apologies in advance. Both of my kids have been kind enough to get sick and infect me, but fortunately Professor Gowdy has offered to step in if either I get too sick to continue or I have not prepared enough material. So either way, he is in strategic reserve. So what I want to do today is talk a little bit about the Pythagorean Theorem. This is hopefully something you've all seen many times, and what I want to do is I want to use this as a springboard to talk about mathematics. So I was a professor before coming here at many places, including The Ohio State University. There is a difference though in mathematics. We don't normally talk about the proof, we normally talk about a proof. And so what I want to do is I want to show you a proof of Pythagoras, maybe show you another proof of Pythagoras. Different proofs have different things to give them value and worth. And I want to get a sense of why might we want to go along this line rather than along that line. So they highlight different aspects. Too often, and I was just saying this a few moments ago with Professor Bocelli at lunch, people just do mindless algebra, and they can regurgitate answers, they can manipulate things, but not necessarily understanding what they're manipulating. And so what I want to do is talk a little bit about how you might take a problem and try to guess what the answer might be, guess what the formula might be. Maybe use some data, maybe use a couple of special cases to get a really good sense of what it might be like, and then try to refine your guess to a theorem. And so we will see the importance of special cases, and of course the specific one we're going to be doing is the Pythagorean Theorem. Alright, so in the interest of full completeness, because I will be posting these slides, I will state what the Pythagorean Theorem is. If you have a right triangle with sides A, B, and C, there is a huge debate as to where A and B should be. This is the right way. A squared plus B squared equals C squared. Okay? Most students know the statement. How many of you know a proof of the Pythagorean Theorem? How many of you have an original proof of the Pythagorean Theorem? Alright, the caliber of Williams students has fallen since the 1800s, as I'll go over in a moment. Alright, so this is one of the standard proofs. Draw a lot of auxiliary lines, as in most geometry proofs. And if you stare at it long enough, it's supposed to work. Sometimes you color code it, and it's, oh yeah. Well, color coding at least tells me now what I should be aiming for. Okay, so probably this stuff here probably equals that stuff. Maybe one of these pieces equals one of those pieces. I'll admit though that this picture does not really say much to me, or say much in a meaningful way. This one is probably true because I found it on the web, and so clearly they wouldn't post something like this. I know I'm supposed to show that this equals that and this equals that, but the actual mechanics of this is a nice challenge. Go through and see if this is correct. There are some fun proofs on the web where you take some shapes, you break it up into squares, you rearrange it, and there's a little bit of a gap. So you have to be careful. So I probably should put maybe proof in quotes over here because I have not checked it. As an aside, when I was teaching Princeton many years ago, I don't know if Professor Goldmacher was in this class, I needed a proof of the transcendence of pi, and I searched the web and I found a web page that had the standard proof. I also found that that person had a 2 to 4 page proof of Fermat's last theorem. Alright, this is one of my favorite proofs of Pythagoras. So we take a triangle ABC and we take 4 copies of it. And we have a right angle here, so we go over A, we go over B, we go up A over B. So we have 4 right angles here, these are 4 right angles here as well. We have a square of side length C. And so one of the things I'm assuming in this talk, and it's going to be very difficult to keep track of exactly what we're assuming as we go on, is that we know the area of a rectangle. So if you have a rectangle that's x by y, its area is x times y. If I cut the rectangle in half diagonally, the area is cut in half. If I rescale a rectangle, if I multiply all sides by alpha, then the area is increased by a factor of alpha squared. So I'm going to assume this basic notion of scaling. And I'm also going to assume that Euclid's fifth postulate, if you look at Euclid's postulates from geometry, this is the one that you have to really pause over. I'm going to assume a rectangle has 4 angles that add up to 360 degrees. And so if I take a triangle, that's going to be 180 degrees. So what I like about this one here is I've got a big square of side length a plus b. So the area of the big square is a plus b squared, so a squared plus 2ab plus b squared. And then that's got to be the area of the square plus the area of 4 triangles. Well, if a rectangle has area AB, then the square is going to have area 1/2 AB. So I get 4 times 1/2 AB. So when all the dust settles, the 4 triangles are 2AB. Adding everything together, we get a squared plus 2ab plus b squared is c squared plus 2ab, or a squared plus b squared is c squared. Alright, other geometric proofs. This is a nice one, so again, the picture we had from before, but just rearranging the triangles in different ways. and now you see that what's omitted here is something of size A by A, something here of B by B, and what's missing here is C by C, so A squared plus B squared is C squared. All right, the last one, as I said, Williams, students seem to have fallen a little bit since the 1800s. So President James Garfield, class of '56, is credited with a proof of the Pythagorean Theorem. For those of you who do small, this is actually why we stay in Garfield over the summer. I will not mention in detail whether or not his proof truly belongs as an original proof or anything like that. All right, so could somebody punch up the screen? All right. If everything works, then having a black image should be effectively the same as hitting mute and not having to walk over there since this is on sensor. Alright, so what I want to do now is I want to talk a little bit about how you might guess the Pythagorean formula, and then once you have a guess, how you would refine your guess and make it a proof. Alright, so guessing to Pythagoras. So A, almost put A in the wrong spot, B, C. So the first thing is, let's guess that there's a linear relationship between the sides of a right triangle. So let's try linear. Well, if it's linear, I can always assume the coefficient of C is 1 by just dividing by it. Otherwise, if the coefficient of C is 0, there's really not that much I'm going to be able to do. All right, so let's say C is alpha A plus beta B. It's the only linear relationship I can have. So let's try to figure out what could we have for the values of alpha and beta. Well, if I send A to 0, then C is going to collapse onto B. So in the limit as A goes to 0, the only way this can hold is if beta equals 1. So send A to 0, get beta equals 1. Well, if we can send A to 0, we can also send B to 0. We get alpha equals 1. Therefore, C equals A plus B. And so if there's a linear relationship, it's got to be A plus B. So all we have to do now is check and see, does this relationship hold? Are there any right triangles you know?
3, 4, 5.
The 3, 4, 5. How do you know it's the right triangle? All right. Welcome to teaching my kids math, 6 and 8. Give me an easy right triangle. 3, 4, 5. How do you know this is a right triangle? You're basically using the Pythagorean formula. Yes?
An isosceles triangle.
An isosceles triangle, okay. And because it's isosceles, these two sides are the same, we might as well normalize them to be 1. And what's the hypotenuse?
Root 2.
Why?
2.
Let's call it 2.
It's
2, right? We're guessing a linear relationship. We are now reduced to showing that this can't be 2. Why is this not 2?
Triangle inequality.
Okay, good. So one is the triangle inequality. That if I have a triangle, the sum of any two lengths has to be greater than the third. Otherwise, I have issues. Why is that? So if you want, think of it as here's one. If they're going up, they're not meeting. This is what Professor Gowdy and I do when he's not yelling or drinking soda. Is we try to talk about why is this illegal. And so we imagine we had a line coming up here. We go up 1 unit. We're drawing our circle, and we're talking about which way the circle curves. And how do we know these don't meet up? How do we know you can't have a 1, 1, 2 right triangle? And again, what you want to say is, well, look, if I've started off here with a 1, 1, if I start moving these out, they're going to move off the line, and there's going to be a little bit of a gap. We want to make that precise. And so making this precise took us a lot longer than we were hoping it would take us. But how do you prove the triangle inequality of a triangle? What do you need to assume for that? That the sum of any two sides is greater than the third, or you have a line segment? Well, one of the things that we figured out we can do is we can do a lot of symmetry, and we can try to understand at the fundamental level what is lurking in the background. And essentially what's lurking in the background is this kind of homogeneity of space. That if we translate a triangle, is that going to change its area? No. If I spin the triangle, it's not going to change its area. If I stretch the triangle, okay, good. So I can do some things and you have change happen. If I rescale all the sides by a factor of 5, then the area should increase by a factor of 25. So what we can do here is we've got this triangle, so we've got 2, 1, 1. One of the things I was trying to talk to Tom and didn't quite get this to work is to reflect it. This would be 1, this would be 2, this is an equilateral triangle, this would have to be 45 degrees and 30 degrees, but how do we know that an equilateral triangle is? So as a nice exercise, can you get a contradiction from an equilateral triangle? The contradiction I will show you, right, so we have here 1, 1, 2. Let's come down now.
Sorry, are you just proving the triangle inequality? Is that what we're doing?
No, I just need to show that this one triangle does not satisfy the linear relationship, and then the linear relationship is out. If we knew the triangle inequality, we'd be done.
Okay.
I'm assuming at this point I don't know the triangle inequality.
And you can't use arguments about walking across a park rather than...
I really want to try to avoid those arguments as much as possible and try to distill it to the most fundamental level of what's going on. If I rescale by a factor of 5, I increase the area by a factor of 25. So, and again, I don't really draw things well to scale. So if this is 45 degrees, 90 degrees, 90 degrees, 45 degrees, this is 2. Right? What's the side down here? Yes? 3, excellent! And I was deliberately trying to draw, why would this be 3? Isn't it 1 by symmetry? Why is it 3? You're absolutely correct.
Because it's 2 plus 2 minus
Yes, we're assuming that if we have a triangle, the hypotenuse of a right triangle is A plus B. So here's A, here's B, here's A, here's B. 1 plus 1 is 2, 2 plus 2 is 4. So this whole hypotenuse has to be 4 units. Because I've just rescaled the triangle by a factor of 2. And now we can say 4 does not equal 2. And that's the contradiction we can use to disprove. If you want to prove that 4 does not equal 2, that's a separate talk. We're going to assume some things, I think. All right, so is everybody happy that we cannot have a linear relationship for Pythagoras? All right, well, if we can't have a linear relationship, what's the next best thing? If it can't be linear, what's the next guess? Quadratic. So alpha a squared plus beta b squared plus gamma ab.
Maybe they're linear terms.
Oh, but then would it be quadratic,
Oh, okay.
right? So I'm assuming I have a quadratic relationship like this.
You want to see squared on the other side?
Oh, I probably do want to see squared on the other side, yes. Yes. Okay, good. So now we'll edit that out. So we have c squared plus beta b squared. Now I'm not going to edit out the laughing as well. This is going to be expensive now. All right, so we've got this relationship like this. What should we do? Is there any coefficient that we can get a sense of easier than others? Which coefficient can we sniff out?
We
Thoughts?
can do alpha and beta.
Yeah, alpha and beta. There was no need to erase it. Right? I'm just trying to fill up time. Right? Send. Do we do alpha first or beta first? Send alpha to 0. No, I'm sorry, send A to 0. Send A to 0. And if we send A to 0, then C has to come to B. The only way that can hold is we get beta has to be 1. We send B to 0, and we get alpha has to equal 1. So C squared is A squared plus B squared plus gamma AB. As an aside, if you know the law of cosines, you can begin to see where something like this might be coming into play, and the generalization of Pythagoras. So if there's going to be a quadratic relationship, this is it. This is the only candidate left. All we need to do is we need to figure out what gamma is. Well, to figure out gamma, we need one right triangle that we know. And if we know one right triangle, we're done. All right, what right triangle should we use?
We don't know anything.
We don't know one here. Which is the one we almost knew? Well, we almost knew the 1, 1. Right? The problem is we didn't know what the hypotenuse was. What's the area of this triangle?
1/2.
Area, good. So we at least know the area is 1/2. Area is 1/2 of triangle. So we don't know what the hypotenuse is, but at least we know the area. Well, what we can do now is we can take lots of copies of this triangle. Let's see if I do this properly. If I take 4 copies of it, these are all going to be right angles. This is 45, so this is a right angle, not drawn to scale. What object is this? Yes, this is a square. What's the area of the square? C squared, and we have 4 triangles. Each of them have area 1/2. So C squared equals 2. So what does C equal? Square root of 2. So we get square root of 2 squared is 1 squared plus 1 squared plus gamma 1 times 1. So the only thing that will work is gamma equals 0. So if there's going to be a quadratic relationship, the only one that will work is when there is no AB term, and it's A squared plus B squared. This was using the triangle, 1, 1, and eventually getting that the hypotenuse has to be square root of 2. You can try to do it with the equilateral triangle and then cutting it down the middle and getting the 30, 60, 90 triangle. I was able to get that to work with a little bit more algebra. The danger is, of course, eventually realizing that you're not getting a special case, but you're actually proving the Pythagorean formula. And if you use, corresponding parts of congruent triangles are congruent, eventually after the dust settles, you can see you can do any right triangle and make the argument work and prove Pythagoras. I want to take one right triangle that I know and use that to then figure out what the formula should be. This is not a proof, of course. This is just, if it's going to be of this form, this is the only form that will work. Okay, so now the question is, how would we prove it? So what I want to do is I want to show the dimensional analysis proof. So, dimensional analysis proof. So, I claim that if I give you a right triangle, the area, let's call this theta, is a function of C and theta. If you know trig, you can write A and B in terms of C cosine and C sine theta. You can get the area. But it's got to be some function of C and theta. We can actually sniff out how the function depends on C. If I double C, what happens to the area? Goes up by 4. If I double C, I double A, I double B. So we know the area as a function of C and theta has to be something of the form C squared times some function of theta. Okay? Almost every good geometry proof I know at some point draws an auxiliary line. Let's draw an auxiliary line. We want to have right triangles. Let's draw an auxiliary line in such a way that we get more right triangles. So we draw the auxiliary line here. Yes?
Tell me again why the area is a function of C and theta? Not
Sure.
A's and B's.
Basically, if you want, once you specify C and theta, you've got a right angle here. Your A is forced down upon you, and your B is forced upon you. So if I specify C and theta, A and B are forced.
By using sines and cosines.
But yeah, by either using sines or cosines, or because I know what this angle is, and I know I've got to go up 90 degrees, I drop down here 90, there's going to be a unique intersection. And so at this point, everything is now uniquely determined.
Perfect, thank you.
Yep. Okay, and so now we have right triangles, so I'll just draw the picture over here. So here is B, here's A, here's theta. And I'm going to give highly unoriginal names, triangle 1, triangle 2. What is, okay, if this is 90, this is theta, this is 90 minus theta, so this is theta over here. So in the two smaller triangles, they're both similar to the original. The area of a triangle is the hypotenuse squared times some function of the angle, so long as it's a right triangle. These are two right triangles with an angle of theta. So area of big is area of 1 plus area of 2. Area of big is C squared f of theta. Area of 1 is A squared, its hypotenuse, f of theta, plus B squared f of theta. because this is a math talk, I have to say one thing before I get to the next line. What do I have to say? F of theta is not 0. So as f of theta is not 0, if say 0 less than theta less than probably pi halves, this will imply c squared is a squared plus b squared. So this is a nice dimensional analysis proof of what's going on. And this is, I think, my favorite proof of Pythagoras. So now, hopefully, I've got, like 30 minutes to talk. I've used 20 to get back to what we already knew. So let's try to push this to a different extreme. There's other geometries you can study. You can study spherical geometry. So imagine now I take a sphere and I draw a triangle with arc lengths A, B, and C. And let's assume that the angle between A and B is 90 degrees. How many people here have seen the spherical formula? What is spherical Pythagoras? Good. I was kind of hoping Professor Gowdy would raise his hand because we've been talking about this. Okay. Because
Same day that we voted on high.
Right. So it took us embarrassingly long to figure out what the spherical formula should be. We Googled it. But I mean, we had some rough idea before we Googled as to what the shape should be. And we tried to figure out, well, what word should we put into Google? Pythagoras spherical, Pythagoras sphere, it wasn't too bad. And it returned the answer very quickly. And when you see the formula, it becomes quite reasonable as to what to expect. I just gave a lecture in 341 today about using spherical coordinates without using spherical coordinates. So today I'm actually going to use spherical coordinates now. The physicists and the mathematicians do things differently. I was a double major. I am completely mixed up. I have no idea which way I'm supposed to do it in which audience. I'm going to use phi as the angle coming down from the z-axis and theta the angle as I'm going parallel to the xy plane. And the reason to do this is if you use these as your spherical coordinates, then when you reduce down to something parallel to the xy plane, you have what looks like polar coordinates. So here is the x-axis, here's the y-axis, here's the z-axis, here's phi coming down, and then theta is going to be going like that. One of the reasons we use radians to measure angles is that if I give you a circle of radius r, and I give you an angle of length theta, then the length of this arc is just theta times r. So if theta is 2 pi, it's 2 pi r, it's the whole perimeter. If theta is pi over 2, you get a quarter. All right, so now what I want to do is I want to look at a spherical triangle. So I'm going to come down A, come down B, and I'll have some angle C between them. And I want to figure out what is the relationship among these quantities. Okay? We know something. The answer is probably going to depend on the radius of the sphere. And the reason is, if I go all the way down to the equator, all the way down to the equator here and over here, I can actually have a triangle with 3 right angles. And in that case, I think all the sides are going to be the same length. So I'm not going to expect to have a squared plus b squared equals c squared. In the limit, though, as the radius of the sphere goes to infinity, if I have a, b, and c of fixed size, or a, b of fixed size, and then look at what c connects them, what has to happen as the radius goes to infinity? So what do I have to get as a special case as the radius goes to infinity? Pythagorean theorem. It's got to reduce to the flat plane. So whatever formula we get, we know in the limit it's got to become Pythagoras. All right, so we have x is r cosine theta sine phi, y is r sine theta sine phi, and z is r cosine phi. So these are going to be the coordinates of a point x, y, z in spherical coordinates. All right, so now I want to find these points. Let's make the points nice. So what I'll do first is the point A, I'll have the theta of A will be 0, and the phi of A, the angle I go down, well, I want the arc length to be A. So it's got to be the arc length divided by the radius, because the radius times the angular measurement is the arc length. Similarly, for point B, I want to have a right triangle, so I'll have its angle be pi over 2, and its angle coming down will be b over r. So I can start writing down the coordinates. All right, so x is r cosine theta. All right, what's the cosine of 0? Does that make? I just want to check and see. Have I confused my notation? No. Okay, good. I have not confused my notation.
I think it's 1.
1.
Okay. So it's 1. Good. So the point is going to be the following. Its x coordinate, cosine of theta is going to be 1. I have an r, and then I have the sine of phi, which will be the sine of a over r. Its y coordinate, I've got the sine of 0, which is 0, and then its z coordinate is going to be r cosine of phi, so r cosine of phi, which is a over r. And as a quick check, this point does have magnitude r, which is good because it's on a sphere of radius r. All right, similarly over here, what's the point here? The point now is going to be r cosine theta. Okay, cosine of pi halves is 0. Then I'm going to have r sine of pi halves is 1. And then I'll have sine of phi, so I'll have sine of b over r. And then finally I will have r cosine b over r. And again, good, this point has magnitude r. It's this point on a sphere of radius r. Excellent. All right, now, if I have 2 points, I can calculate the angle between them. So if this is VA, and this is VB, and this is the angle between that, the cosine of the angle between them is VA dot VB divided by the length of VA, the length of VB. Well, what is this angle here? That's going to be my arc C. That's going to be its length. So this angle is going to be C over R. So I get the cosine of C over R equals, these lengths are both R, so I get R times R. Now I have the dot product. Good, 0, 0, excellent. I get R squared cosine A over R cosine B over R. The R squareds cancel, and you're left with cosine of C over R is cosine of A over R cosine of B over R. This is spherical Pythagoras. Now we said that spherical Pythagoras should reduce to regular Pythagoras in the limit as r goes to infinity. Well, let's Taylor expand. So if we Taylor expand, let's only keep the main term. So we'll use the cosine of u is 1 minus u squared over 2 factorial plus dot dot dot. So we get 1 minus c squared over 2r squared plus dot 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 is 1 minus a squared over 2r squared plus dot 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 times 1 minus b squared over 2r squared plus dot dot dot. The 1's cancel from both sides. The dot dot dots will have at least a 1 over r to the 4th. Won't matter in the limit. I multiply through by 2r squared, multiply through by negative 1, and you get c squared is a squared plus b squared plus an error of size 1 over r squared, which will go to 0 in the limit. So this is Pythagoras on a sphere. This gives us the limit as r goes to infinity. We recovered the plane. So a sphere is actually a surface with constant positive curvature. You could consider a sphere with constant negative curvature. This would be a hyperbolic space, the upper half plane, the unit disk model. Anybody want to guess what Pythagoras should be in the hyperbolic case? What would you guess? Yes?
Some formula with hyperbolic cosine.
Yeah, basically just shove in an h after all the cosines. And how do you tell if that's correct? Google! And so, as soon as we did this, well, the next thing we did is, well, what should it be on a hyperbolic space? We probably put in the letter h. And we did a quick Google and turned out yes, right?
I think actually you said put in the H, I said, oh, that's stupid. You were right.
Oh, I was doing the cleaned up version. He also said something about hating little kids and. So it's exactly what you would expect. So then the question becomes why? What's going on here? How does it pass? Well, if you think about the connections between cosines and hyperbolic cosines, there's a lot more that you can say in stuff like this. So to just quickly recap, what I hope you saw today is the power of dimensional analysis. Is we can start with something we know, start with a problem that we've seen many times, and the reason Professor Gowdy and I were discussing this so much is we realized there's a lot of math we saw when we were little that we just, I think, absorbed and then just moved on and didn't really dwell on nearly enough. And you can correct me if I'm wrong. And that just, when I first saw the Pythagorean formula, I didn't really stop and think about it as much as I should have. I wasn't really asking questions, well, what's next? How else could it be? What would it be in other places? And it was just really fun to explore and see what was going on. And as soon as you see the answer, the answer pops out immediately. And then to see the power of knowing, one special case and looking at the consequences. If there's just one triangle we can understand, we can then use that to fix the constants. But it's not so easy to find that one triangle. And then you're coming down to, well, what do we need to prove the following? What do we need to prove that the sum of two sides of a triangle is greater than the third? And just trying to go back. Next fall, I'm going to be teaching complex analysis. I hate the first half of the class, I know this is being recorded, because I never remember what we have proven up to a certain point when we're trying to get to Cauchy's residue theorem. And you have these chains of things as to when do you know something, when can you finally conclude. And at the end of the day, you've got the theorem and you always use it. But sometimes it's worthwhile just taking a step back and thinking, what did you really need, what was really going on? And so fundamentally what's going on here is how space works. If we rescale things by alpha, the lengths increase by a factor of alpha, the areas increase by a factor of alpha squared. That's what goes on in a plane. I can translate, I can rotate, it doesn't change. What happens as we go into a sphere? How does the geometry then change? So, thank you.